Section 3.4 is solving multi-step inequalities. I can solve multi-step equalities. That's our learning target and what we're shooting for in this section. Big ideas for this section. In the same way multi-step equations are solved using properties of equality, multi-step inequalities are solved using properties of inequality. The properties of inequality are used to transform the original inequality into a series of simpler equivalent inequalities. So in example 1, we're going to look. My variables being multiplied by 4 and added by 9. Just like with equations, I get rid of any adding or subtracting first. Right now I have a positive 9, so I subtract. And again, whatever we do to one side of our inequality, we have to do to both. 9 minus 9 is 0, so I'm just left with the 4t greater than 12. Now, my variables being multiplied by 4, I get rid of multiplication by division. Uh, 4 divided by 4 is 1 times t is t. 12 divided by 4 is 3. Now, since I divided by a positive 4, my inequality just drops down. I don't have to flip it, and I get t is greater than 3. Here, when we check it, we check both our boundary point and our inequality itself. So to check our boundary point, we plug in our number here. So 3. 9 plus 4 times 3. And it should equal 21. Remember, when we're checking our boundary point, that boundary point is what splits the graph. Everything to one side is greater, everything to one side is less. So it's where it's equal. Here we did get 21 equals 21, so we are good. 3 is the right boundary point. Now we're also going to check our inequality to make sure it's right. So we said are all numbers greater than 3. So let's check a number greater than 3, like 4, for example. So 9 plus 4 times, I'm going to plug that 4 in for t, should be greater than 21. And I get 25 is greater than 21, which checks, so we are correct. Both our boundary point and our inequality symbol are correct. Now, feel free to pause here and give this a try if you'd like. Right now, our variable is being multiplied by -6 and subtracted by 7. We get rid of any adding or subtracting first, just like we did with equations. Again, we're going to do PEMDAS backwards. And whatever I do to one side of my inequality, I have to do to both. -7 plus 7 is 0, so here I just have -6a is less than or equal to 24. Now, my variable is being multiplied by -6, so I get rid of multiplication by dividing. -6 divided by -6 is just 1, so I have 1 times a is a. 24 divided by -6 is -4. Now, since we divided by a negative number here, we have to flip our inequality, and we get a is greater than or equal to -4. Now, to check it, I plugged my boundary point, -4, in equal to 17. Again, our boundary point should have an equals and give us a true statement. And then I plugged in a number greater than -4, like 0 here. And I got -7 is less than or equal to 17, which is true, so my inequality is true as well. For B, n is being multiplied by -3 and added by 5. We're going to go ahead and get rid of that addition first by subtraction, using that subtraction property of equality. As long as we do it to both sides, it stays equivalent. 5 minus 5 is 0, so what I'm left with is the -3n. Don't forget to bring that sign down with our number. And a -9. Keep my inequality. We only ever change our inequalities if we multiply or divide by a negative number. So anytime we add or subtract, we keep it. Now my variable is being multiplied by -3. I get rid of multiplication by dividing. 3. -3 divided by 3 is 1 times n is n. We look here. Because I divided by a negative number, I have got to flip my inequality. So I have 3 is greater than n. Here I went ahead and checked both our boundary point by plugging in 3 equals. Both sides should be equal there. That's true. And then I checked my inequality by picking a number that makes this true. 3 greater than 0, for example. 0 is the one that I used because it's a pretty easy one to calculate with. And I got -4 is less than 5. That's true, which means our inequality is true. For C, x is being multiplied by 0.8 and added by 30. So again, we're going to do PEMDAS backwards. We get rid of everything that's not a variable term. To get rid of addition, we subtract. And whatever I do to one side, I have to do to both. 50 minus 30, 20. Keep our inequality, and I get 0.8x because 30 minus 30 is 0. Now, x is being multiplied by 0.8, so I divide by 0.8. Here I get an x. Here I get 25. And we check. Because I divided by a positive number, I drop down my inequality. I do not have to flip it. Here I checked both my boundary point by plugging in 25 and setting it equal to each other. Checked. We're good there. And I checked that my inequality was right by picking a number that 25 was greater than. So 25 was greater than, again, I picked 0. We could have picked 24. We could have picked a -100. Doesn't matter. Any number that makes this inequality true. And when I plugged that in, I got a true statement here. 50 is greater than 30, so our inequality is correct as well. In the community garden on page 187, you want to fence in a vegetable garden that is adjacent to your friend's garden. That means they're right next to each other, sharing a side. And your friend's garden is 12 feet wide. You have at most 42 feet of fence. What are your possible lengths of your garden? So, if our friend's garden is 12 feet wide, we're going to have some garden here. And it's going to go next to our friend's garden, which is over here. And we know that our friend's garden is 12 feet wide, which means our garden also has to be 12 feet wide. And if we're talking about fence, okay, we're talking about perimeter. So our formula for perimeter is 2L plus 2W. But we don't want it equal here. We want our perimeter 2L plus 2W. We have at most 42 feet of fence. So at most means we could spend or use all 42. We could use less. Let's say we only wanted to do 30 feet of fencing. Maybe we wanted a smaller garden. But we can't use 50 feet of fence. It can't be any more because we only have 42. So this right here is our inequality we're going to use. Now, we know what our width is. We know our width is 12. So I'm going to plug that in for W. And now we can solve. My left side is not as simple as I can get it, so I'm going to go ahead and do that first. My variables being multiplied and added, so I get rid of my addition first by subtracting. Gives me 0, so I have less than or equal to 18. Now, I have multiplication. We get rid of multiplication by dividing. I divided by a positive 2, which means I keep my inequality. So our possible lengths are less than or equal to 9. If I used 9, okay, all the way around, I would use all 42 feet of fence, but I don't have to use all, so I could make it not as long if I didn't want to. So lengths less than or equal to 9 feet. Now, you want to make a rectangular banner that is 18 feet long. You have no more than 48 feet of trim for the banner. What are the possible widths of the banner? So we're talking about a rectangle and the trim, which means that's the part that goes around. So we're talking about perimeter. Our formula is 2L plus 2W. But we don't have to use the whole thing. So our perimeter, we have 48 feet of trim. No more than that though. So we could use all 48 if we wanted to. And then think about it. Could we use 40 or could we use 50? Well, we could use 40, but we can't use 50 because we don't have 50. So the amount that we use has to be less than or equal to 48. We know that it's 18 feet long, so my length is going to be 18. So 2 times my length plus 2 times my width has got to be less than or equal to 48. My left side's not as simple as I can get it. I can go ahead and multiply first. And now both sides of my inequality are simplified, so I can go ahead and solve. My variables being multiplied and added, so I'm going to go ahead and subtract first. Now to get rid of my multiplication, we can divide. And again, because I divided by a positive number, I can keep my inequality, and I get my width is less than or equal to 6 feet. So I could use 6 feet width, and that would use all the trim that I have, or I could go slightly less. I could go 5. Maybe I only want to do 1 foot wide. That would work too. So our possible widths are less than or equal to 6. Keep in mind it can't be a negative there. Just like on the last problem, we couldn't have actually had -4 because we're talking distances. But anything less than 6, that is still positive. In example 3, we want to determine whether each number is a solution. And I have 4 different numbers I want to check here. So I can either plug those in every time and solve, or we can work a little smarter, not harder here. Solve my equation for my variable, and then it's a lot easier to see right away whether or not it's true. So we only have to solve it one time. When I look here, my left side is not as simple as I can get it. I can distribute first. So I take 3 times t, and I take 3 times 1. My left side still isn't as simple as I can get it because I have like terms. 3 minus 4 gives me -1t. I still have that plus 3. And I haven't done anything other than simplify my left side. So I don't change my inequality or mess with that. I don't mess with my right side. And now I finally have a simplified left side, a simplified right expression, and we can solve. My variable is being added by 3 and multiplied by -1. We always get rid of any adding or subtracting first with PEMDAS backwards. We want to try and get all of our variables on one side and our number parts on the other. So here I have -1t. 3 minus 3 is 0. And -5 minus 3 is -8. My t is being multiplied by that -1, so we divide by -1. And I get t and 8. But my inequality here, we have to check anytime we multiply or divide. It's being divided by a negative number, so when I bring my inequality down, I have to flip it. So, solutions then are going to be any number that is less than or equal to 8. So in A, is 8 less than or equal to 8? Yep. So is this a solution? Yes. Is 9 less than or equal to 8? No. So it's not a solution. Is 10 less than or equal to 8? No. So it's not a solution. And is 11 less than or equal to 8? No. So it is not a solution. And that was way fast, quick, and easy compared to having to solve every single time. And I'll continue on in another video.